welcome to our colloquium for this week. My name is Bruce Darling. I work as the Associate Chair for Education in the department, and it's my pleasure today to introduce Professor Chris Rudell. Chris joined our department back in 2009. He got his bachelor's degree from University of Michigan in Ann Arbor, and then his master's and PhD from UC Berkeley afterwards. He's worked out in industry for a little while as IC or RF IC designer at Berkana, which I guess is now part of Qualcomm, and has also spent some time with Intel and their developmental labs. He's also been very active in terms of a lot of the premier conferences in this area, the International Solid State Circuits Conference, and the most recently the RFIC, which I guess Chris has been on the program committees for that for almost a decade or so. So he's very well steeped in all of that, and was also our local chair for the RFIC symposium just this past summer in Seattle. And I guess he's regaining his composure after that trial by fire. Yeah, that's running a conference of that size is a lot of work. Anyhow, without any further ado, I'm very happy to introduce Chris Rudell.
Thank you very much, Bruce. And it's certainly a pleasure to present here. It's actually my first time presenting at a colloquium. I see many faces I recognize from my classes, and so hopefully I won't bore those people because they probably have already seen a lot of this material. As I go around, and I've given this talk in a number of locations, mainly some of the big guys like Google and Microsoft and Qualcomm. And a lot of people ask me, they're sort of interested in the title. It sort of sounds like a fancy title that tries to fit in with the era of big data. There's a lot of talk about big data here at the University of Washington. And what in the world do chips have to do with big data? Is this just a way to sell myself, maybe to get better funding, or is there something really here? And I actually believe that there's something really here because a role for chips to play, mainly because what we're going to be dealing with is really large amounts of data that we're going to store, acquire, maybe through sensor applications, and more importantly, we're going to slosh that data around, transmit and receive, either wirelessly or over a wireline system. All right, and so that's really where chips will play a role and will enable a lot of big data type technologies and in moving this data around. Now, perhaps by example, one area where we could look at where chips really enabled software. Okay, today it seems obvious. There's a huge industry out there, a huge community of people that are writing software apps for cell phones, right, for smartphone applications. And if we rolled the clock back 30 years and really look at how chips played a role in the modern cell phone, what you'll realize is we go back to 1979, one of the original cell phones from Motorola. This is the famous cell phone in that movie Wall Street. If you opened up that cell phone, there would be a board in there with a collection of discrete components, and then the whole backside of that brick phone was battery, just to drive the transceiver, and that was the only thing that it was powering. It wasn't powering anything else. It was an analog transceiver. And over time, there was a lot of research on how to take all of those components and cram it onto a single piece of silicon, all right, and shrink the form factor of that phone. And so these are some works that I've been involved with over the last 15 years. This was something we had at Berkeley. This was the first, it was an effort that I led. It was the first CMOS integrated receiver for something called the DEC standard, which really evolved from Europe, but it's most analogous to the modern Wi-Fi standard in terms of performance, or Wi-Fi receiver. Then a few years later, we actually realized or implemented the first fully integrated transceiver for a cell phone application. And as you move from really short-range radios to longer-range radios, the performance that's demanded out of the front end rises in terms of common metrics for analog components like synthesizer phase noise, dynamic range, linearity, noise figure, et cetera. Anyway, so this was really a very, I would argue, a difficult high-performance transceiver, cellular transceiver. And it was all integrated for a common standard GSM in North America. If you have an AT&T phone, your voice data is transmitted over GSM. All right, so everything's fully integrated there. And then moving along, about 2005, this was actually the commercial version of that. That's taking that chip that we had at Berkeley and realizing it in a startup. And that was really the first production GSM transceiver. And then our company was bought out by Qualcomm. Now that last chip I was not involved with. That's actually just a recent publication. And for illustration, it's what people are doing now, certainly in industry, of realizing these transceivers on a chip. And what we notice is the level of integration as we move from, say, 97 over to 2011, the level of integration and shrinking the form factor of that transceiver has quite a bit has happened, where it's difficult to maybe realize just the receiver, and then on the right, just a corner of that chip realizes an entire transceiver. That actually has multiple transceivers on that chip, along with a lot of digital logic for computation and signal processing. Well, concurrent with this integration, what have we had? We moved from that old brick phone, and then about 2000, this is really just a cell phone, but it's highly integrated, and the form factor is very small. The point being of all of this, how would this fit in with big data, and how does this fit in, maybe with software? Where is the real development happening in these phones? It's happening in software right now. It's not happening in the chips. How to do this chip and how to integrate this, that's fairly well known now, and it's being really handled by industry. And it's not so much of a research topic, although there are some interesting research topics that are left. But the point being that this integration really freed up room on this valuable space on the board of your phone to allow more powerful processors and more memory, okay? And then that is what really led to the modern smartphone and really all of this software and programming that is taking place, and that's really the hot area. But it was all enabled through this integration and really research on chips and architecture and new types of circuits, okay? So what does a group like mine actually do research on? All right? What is it, the big picture, the 100,000-foot view of what's going on? Well, what we like to do, groups like mine and Professor Otis and several other groups at other universities, Dave Allstott was also in this space, and basically, we have this logic, this technology, this silicon technology called CMOS, right? We use it to implement logic. It makes a very good switch, all right? I have a transistor, I can turn it on, I can turn it off. It's really built in a large, I would say probably 90% of the devices that are fabricated out there are CMOS technology, okay? The technology is really built for digital logic, computation and signal processing, et cetera. We want to do things in the digital domain because of reasons related to noise immunity, et cetera, and repeatability and computation. Now, the challenge really in my field is, how do you realize, we all know that, yeah, it's great to do, digital programming and logic, but we live, they say, in an analog world, all right? So somehow we need to interface this digital to the analog world. And there's, a number of applications that we see here. We could talk about biomedical applications, neural interfaces, wireline, wireless transmission, maybe control for MEMS interface. Now, the technology, again, this CMOS is really built for digital, all right? And what we would like to do is figure out ways of realizing analog circuits and these interface circuits using standard CMOS technology. And then that's a big win, right? Because now we can take this analog function and integrate it with the digital, collapse it into one chip. The form factor is smaller, it's cheaper, and it's easier, particularly like for biomedical applications. At the Neural Center, we have a project in our group right now. It's easier to implant these devices in a body because they're very small. Okay, so again, the challenge is realizing these analog mixed signal functions in this technology that's really not built for analog circuits. All right. So now, what are some of the trends in terms of CMOS technology? I'm sure many of you in this room understand this plot, but basically this is just showing Moore's law in action. All right, so the good stuff that's going on, and over the years, through Moore's law, we've shrunk these devices. The minimum dimension of a transistor, CMOS transistor, is decreasing roughly by a factor of 2, or has over the last 40 years. They say we're now entering the end of the Moore's law era. So we're not shrinking them quite so fast anymore, and at some point we will hit a wall. But generally speaking, this trend has held over 40 years. So the device technology, the minimum channel length, has shrunk, all right, and there's predictions going forward. And then the device speed has also, as we shrink by a factor of 2, it roughly increases by a factor of 2 because our parasitics are now becoming smaller. So we measure that in terms of this figure of merit called an FT. It's just roughly the fastest speed that we can run the device at. And you can see that back in the 90s, right, where FTs of these devices were sub 10 gigahertz. And that was the first time that people started exploring, realizing radio circuits, like for Wi-Fi and cellular, in standard CMOS technology. Initially, people thought, certainly guys like me were crazy, and groups that I worked in were crazy to do this. But that was where it became plausible. And now, as we get to the year 2000, now we're talking about 100 gigahertz, so people started exploring, initially millimeter wave, implementing millimeter wave transceivers for communication and imaging applications. And then going forward, we're going up into the terahertz domain. So this all looks great, certainly for analog circuits. We shrink the device, and we can run it faster, and that's also good for digital circuits. However, there's some challenges here. Because we're shrinking the dimension of the device, long story short, for reliability reasons, the voltages between the different terminals of the device must remain below some level, basically to minimize the possibility of what they call gate oxide rupture. So the supply voltages have been dropping as the technology is scaling. Well, that's great for digital logic, right? Because basically, if you think of it in terms of CV squared F losses, we can reduce the power and run this thing faster, right? But for analog circuits, that's really defining the higher end of the dynamic range, right? So I really have this moving target. It's hard enough to get a lot of these applications and circuits and architectures in CMOS, analog mixed signal. But then on top of once I figure it out, then now, every time I move to a new technology node, there's a new set of challenges. And that's actually what keeps the field active in terms of research and development. It has been active for the last 30 years. In addition, all right, so we have this challenge with respect to the high end of this dynamic range, and then the fundamental gain that I can get out of a single transistor, what we call the GMRO. Long story short, the GM of a device, the transconductance, that is remaining relatively constant, actually improving a little bit. But the RO, as we shrink the channel length, the output resistance is vastly decreasing. So the amount of gain I can get out of a single device is really decreasing. Back in the 90s, it was like 100. So building an op-amp with an open loop gain of 100,000, no problem. Now we're talking about GMROs that are less than 10. So that's a whole field of work that people are looking at is, how do you replace the function of a standard op-amp using something else to realize maybe like a switch capacitor circuit? I mean, it's a very challenging problem. So again, the technology is becoming, I would argue, increasingly hostile towards analog circuits. So that's what actually makes this field sort of fun to work in and a lot of interesting problems. And then on top of it, there are new evolving applications, i.e. this big data and how we're going to slosh around lots of data and have very high bandwidth connections. All right, so of course, I don't do any work anymore. I seem to just write proposals and teach and that kind of stuff. But I've been very fortunate. I have a collection of students over the last 5 years. They've done some great work, and I've been fortunate to work with a great set of students here. We'll talk about their individual projects as we go along here. Okay, so now that we have this big picture, what are some of the things that we've been working on in our group? And again, this idea of very broadband transmission, wireless transmission, and enabling higher data rates, maybe to address future big data applications. And one project that I've had, my first PhD student, Venu Bhagavatula, has worked on this idea of a very extremely broadband, ultra broadband millimeter wave receiver. And we'll talk a little bit about that. Actually, through his PhD, we came up with a number of interesting techniques that I think are pretty cute. Anyway, we'll go into that. We have some nice data from that. We're actually still publishing some papers. Then I have had a project, and this project is actually going to expand going forward. I recently got several sources of funding, one of which is NSF, for radio coexistence. Basically, we'll talk about this in a second. Right now, we're trying to utilize the spectrum as best we can. There's a finite amount of spectrum, particularly in the RF bands, 1 to 5 gigahertz. We're stacking up and transmitting and receiving many things, sometimes even simultaneously. And a radio, for it to exist with all these interferers around, building such a radio, again, in silicon is really challenging. So we have a very interesting project, I think, on TX to RX self-interference cancellation. That's a hot topic at the moment. You may have heard of the whole idea of full duplex radios, transmitting and receiving on the same frequency. It's kind of futuristic, but this is in that vein. And anyway, we'll talk a little bit about that. And then one of the first projects I had here at UW, this was a transceiver for long-range sensor communication, okay? And then a little out of this vein, maybe, of big data, is I have a joint project with the radiology department here at UW, the medical school. It's a dense PET imaging, positron emission tomography array that's just realized in silicon. We actually just got this chip back. It's pretty interesting, but actually it does fit into the theme of big data, because these guys in the imaging community, they're looking at trying to collect as much data from a detection array, imaging detection array, and then they get this into the digital domain, and they're coming up with all new methods of digital signal processing to better analyze or construct an image. So more efficiently being able to get that data from the detectors back into the digital domain. That's a big problem that people are struggling with, and that's in this vein right here. And then the last topic is actually one my student Eric Pepin and Daniel Micheletti. They've been working through the Neural Center. Again, it fits great in this theme of CMOS integration. Anyway, I'll leave that till later. Basically, long story short, implementing a neural stimulator. These things typically, the drive voltages are 30 to 50 volts, but now trying to implement that in a technology where the transistor is supposed to have a voltage across it of no greater than 1.5 volts. All right, very challenging problem. And I have a couple of students that are looking at that right now. Okay, so again, in this theme of, somehow going forward, we're going to be sloshing around a lot of data, whether we're talking about the internet backbone. Companies like Google are very interested in what we call the E-band. That's like 70 to 80 gigahertz. People are exploring that for point-to-point communication, high data rate communication, maybe even last mile to the home, and then even from your device to a very short-range communication to a base station around your home. All right, so where are we going to get more of this bandwidth and data? Well, that really is going to come from, not just implementing chips, but there's several ways to do that. There's research on new modulation schemes, new networking schemes, a variety of areas. But in terms of the hardware and the chip, that's the problem that I'm interested in, is how could we enable more bandwidth? And my big picture view of what are the challenges of getting more bandwidth, particularly from the front end, I sort of break it up, the spectrum up here, into what we call the TV white space band, and then maybe in the RF bands, where these are where all the commercial standards are, and then going up in frequency into the millimeter wave band at a very high frequency. So each one of these regions, they have advantages and disadvantages, particularly with respect to implementing the hardware. At low frequency, recently there's been some bandwidth that's opened up from the old NTSC standards, the TV standard, analog TV standard. People are exploring using those for more like Wi-Fi transmission. In the RF band, not a lot of spectrum available, very crowded. All right, but there's some opportunities in here, guard bands between transmit and receive bands. They call them the duplex band. It's just a dead frequency region. Somehow, if we could utilize that, or potentially transmit and receive at the same frequency, as I mentioned earlier, in full duplex, that could open up more bandwidth. And then, of course, at higher frequency, there's actually a lot of available bandwidth in certain bands. 60 gigahertz is one of them. 70 to 80 gigahertz is another, and then beyond 100 gigahertz, there's also a lot of bandwidth available. Now, the challenge is, as you're lower in frequency, the path loss as I transmit from point A to point B is lower. So as I go way down here, it's pretty interesting. All right, so I have low loss here. It's still reasonable in the RF bands, but up at millimeter wave frequencies, the path loss is very high. All right, and that's challenging to implement the transceiver. You have to do things like implement phased array systems. All right, and then from the perspective of realizing the chip, at really low frequencies, the radio front end, the passives, like the L's and the C's that we'd use to resonate our circuits, they become prohibitively large because we're operating at such a low frequency, prohibitively large to integrate in silicon. So you have to look at other techniques, maybe just running the thing broadband, but then that burns a lot of power. In the RF bands, it's pretty reasonable. And then as we go up into these millimeter wave bands, it's actually very nice because the frequency is so high that the passives shrink to very small dimensions, and they're very easy to integrate in the form of silicon. All right, so we'll talk about, let's talk about this millimeter. I have projects that are really, really concentrated in these two regions right here. I forgot this bulleted item, but we talked about these. But anyway, in these two regions, the RF band and up in the millimeter wave band. Again, trying to explore ways of getting more bandwidth. So the first project I'd like to discuss, this is the one that Venu Bhagavatula led. He just recently graduated with his PhD, and he's at Samsung doing RFIC design. He just started a couple of weeks ago. And he worked with a couple other of my students, Tong Zhang, who I believe is here, and Apsara Sarvana, who is now at Qualcomm in San Diego doing RFIC design. And so, generally speaking, what are the trends in this millimeter wave band? Maybe some of you have heard of the 60 gigahertz standard. All right, that was envisioned maybe 10 years ago for short-range, high data rate communication. In large part, in my opinion, the 60 gigahertz standard has struggled. And the main reason is, in my opinion, is the data rates that it offered 10 years ago, that they were very interesting. But by the time people figured out how to realize the chip, and in particular, the solutions they came up with were very power hungry because they were operating at such a high frequency. And in that time, 802.11 evolved, all right? We have new flavors of 802.11, N and AC, which is just coming out, which have data rates that are starting to approach something like 60 gigahertz. It's at a lower frequency, so the power consumption in chip form is significantly lower. So for portable devices, that's interesting. So going forward, in the millimeter wave band, what we wanted to look at is, again, something that's very integrated, maybe not 60 gigahertz, which is short range, but longer range in the E band, point-to-point data communication or last mile, which implies more directionality if I have a phased array beamforming system. All right, and that implies more elements in the array, and that's a problem from the power. That goes contrary to lowering the power. Some more elements in the array, and of course, this idea, I want to go beyond the bandwidth that's offered by something like 60 gigahertz, 2 gigahertz channel bandwidth. I want 20 gigahertz channel bandwidth. That was the initial goal that we started this project off with. And that implies, very low Q circuits, or circuits with what is kind of recently in my community, people have been describing as high fractional bandwidth, the bandwidth of the signal relative to the center frequency, sort of analogous to the term Q. So again, the real challenge here in this project was power consumption. How, through the architecture maybe, and maybe new circuit techniques, how can we inherently lower the power of a high element array that's very wide bandwidth? All right, so if you look at some of the, when I started, my background is really in the RF area and integrating RF radios for commercial standards when I was a PhD student, and then I went out into industry. So this millimeter wave stuff was new to me. And so when I read the publications, I found them interesting. This is, maybe what you would typically find is a direct conversion, what we call direct conversion, where you'd have a set of receivers that make a phased array system that we do beamforming either on the receiver or the transmitter. The more elements we have, the better we can form a beam or add more directionality. And now in these systems, so what they use is typically direct conversion, where we have our incoming signal, and then using a single local oscillator, we do a direct down conversion to baseband. The signal goes into the digital domain, where we then demodulate it and grab our data. Now, this is really, what I found this is interesting is 20 years ago, people were exploring ways to try to realize direct conversion receivers for RF applications, because what that did is enabled integration as a small form factor in chip form. So I found it interesting. I thought there was some legacy there that people were trying to apply this same methodology to phased array systems. Now, the problem or the big difference is if I have an RF radio, I just have one channel. All right, or a set of IQ mixers. But now if I want to make a phased array system with 4 elements or 8 elements, 64. I'm going to replicate all of these guys that many times. All right? And so the real challenge that people have been struggling with is this local oscillator has to be distributed across the chip and feed all of those mixers and all the parasitics that go along with it. And that's one of the big reasons why these things are very power hungry. So we actually, we played with this a little bit initially. And what we started realizing is that going backwards, sort of in if you know radio architecture, a super heterodyne architecture is one of the first architectures that people like Armstrong realized in radio form. If we actually went backwards and realized a heterodyne receiver where the conversion is done in multiple steps. So we'd move, this would be our millimeter wave signal here, band, and then we do a down conversion through the array where we're doing our phased array system to a common IF. And we do this using a much lower frequency oscillator. Then we go into a common IF path, and now we only have a single down conversion to baseband, and only a single set of mixers that down convert the signal to baseband. And that can be run at a high frequency because now it's one set of elements instead of 64 or whatever number for a very high element array. Okay, so this is what we started exploring initially, so it looked interesting. But again, now another subtle point is that this goes contrary to the theme of having a very wide bandwidth signal. All right, so what we need to do is pass this wide bandwidth and maintain a very wide bandwidth all the way through up at millimeter wave, the IF stage, and down at baseband. And that's a challenging problem. One way you could think of that is what we realized is the IF stage was becoming problematic. I'm sorry, was there a question? Oh, okay. What we realized was that what became problematic is really the IF stage and this concept of high fractional bandwidth. So if you look at, if I'm trying to grab 10 gigahertz around 50 with a center frequency of 50 gig, I've got a fractional bandwidth that's going to be 20%. But as I bring that IF frequency lower, now the fractional bandwidth of the IF is really growing. So you could argue, all right, well, I saved a lot of power in the LO distribution, but now I created a new problem at my IF stage. I'm going to have to build some very complicated circuit that could be potentially power hungry and use a lot of silicon area to maintain this high fractional bandwidth. So, my student Vinu's PhD, it really started actually at Broadcom. He started his PhD 4 years ago, 4.5, in their advanced development group. He did an internship, and they realized a really high bandwidth IF stage for a 60 gigahertz radio. I was actually exploring using that for commercial parts. So he started playing around with LC tanks and resonating LC tanks, which is not a new concept. But anyway, he has some nice work in his thesis where he's basically shown, try to make a long story short, if I try to use a single LC resonant circuit to resonate a node at the output of an amplifier, I'm going to cascade several of these stages down through my receiver. There's really a limit in terms of power and gain. There's a high end of what you can do in terms of the amount of bandwidth that you can realize, how much you can DQ that circuit. And maybe in the interest of time, I'll skip that a little bit, but one thing that he did explore, again, this is not something that's necessarily new. People like Francesco Silvetto, John Long, and several other groups over the last 8 years have applied what they call transformer-based feedback to realize broadband circuits. So instead of LC resonating a node, we use a transformer and we put it in a feedback path. And as many of you know, one benefit of feedback is it can broadband our circuit. All right, so anyway, in his work, at Broadcom and afterwards, he really explored modeling these transformer-based feedback networks. And long story short, there's different flavors of transformer-based feedback. There's a source-to-gate transformer feedback. There's drain-to-gate transformer-based feedback. Anyway, there's several ways of doing this, but the method that he used and is more popular for stability reasons is this source-to-gate transformer feedback. And anyway, he came up with some nice ways of modeling in his thesis, and he had a nice paper at ISCIS on really, exploring really what are the trade-offs and the amount of feedback that you apply and what the implication is for power consumption and bandwidth and stability. And then based on this work, what he did is he actually realized this IF stage. Again, the circuits were not necessarily new for this. It's a fairly broadband circuit at 10 to 12 gigahertz for a 60 gigahertz radio. But he did come up with some new layout techniques, and he actually he realized a chip, and we had a set of papers, one of which was at the RFIC symposium, followed by a transaction paper in microwave theory and technology. This guy was implemented in a 50 nanometer process, and it had, in terms of noise figure, bandwidth, power consumption, it was very competitive with other publications that were out there. However, this gave us 2 gigahertz at 10 gigahertz. We were really after, in this PhD, is expanding this thing to like 20 gigahertz. So this is really kind of more of the conventional. So when he came back, what we did is we started exploring other techniques to really getting more bandwidth. There's things that are really new, okay? And so the first thing we explored is area-optimized distributed amplifiers. One of the things that distributed amplifiers are not new, okay? Realizing them in silicon is very challenging. Long story short, they can give us something very broadband, but long story short, these inductors that you see here, they use a lot of silicon area, all right? And that's expensive, all right? And it's rather impractical. So what my student did is actually, it was pretty interesting. He started with everybody implements a low-pass distributed amplifier, but a much lesser version of this is a bandpass distributed amplifier, okay? Now, remember, what the goal here is to reduce the amount of inductors that we have in there that use up the silicon area. So we started exploring this guy, and at first glance, you'd take a look at this and you'd say, well, I just took 1 inductor and made it into 3. So it doesn't appear to be moving us in the right direction. However, the thing to focus on is these 2 shunt inductors right here. And so we looked at this bandpass DA, and then using another technique, that you probably could find in a journal back in the 1930s or 40s. It's called a Norton transform. You've heard of Norton equivalence and a Norton source. But this is another technique to create an equivalent circuit. So what it does is it takes this floating inductor and transforms it into 3 inductors plus a transformer. All right, and the relationship between that inductance and the resulting inductance after the transformation is described by these guys right here. And mainly the thing to focus on is the turns ratio on the transformer, N. All right, now again, at first glance, we took 1 inductor and turned it into 3 plus a transformer. Definitely not going in the right direction. If you think inductors take a lot of silicon area, transformers take that much more silicon area. So it's very painful in terms of area. However, if we look at the way this was synthesized is, if you look at the top form, that's your standard second-order canonic form of a bandpass filter, and then you take this L2 and you basically break up. You break up L2 into 2 equivalent components that are L1. Give me a second here. L1 shown here. So you break it up into L1, and then there'll be some residual inductance, Lx. Then you apply Norton transforms to these 2 L1s, and you use a turns ratio of 2. What ends up happening in the terms of this 1 equivalent inductance after the Norton transform is you end up with a shunt inductor that is a fictitious negative inductance, minus L1. All right, and then now we've got 2 of these guys, and if we rearrange this again, we'll end up with 2 back-to-back transformers with the same turns ratio. All right, but now if I have back-to-back transformers with the same turns ratio, that's equivalent to just shorting this node to this node and this node to this node. So you knock out the transformers, both of them. And I have a minus L1 in parallel with an L1, and what does that do? That knocks out the L1. All right, so that now is removed. And the equivalent circuit is now shown at the bottom. Again, I started with 3 components up here. And here I have 6 components resulting inductors. So you'd still argue, well, what did that do for us? Well, what it did for us is the value of these inductors have been significantly reduced relative to L1 and L2 up above by a factor of 10, okay? As much as a factor of 10. So realizing those, even the comprehensive inductance is in silicon is, you can make it, basically the area that's used by the inductor is related to the value of the inductance. So because we've dropped that by a factor of 10, we've also dropped the area that this distributed amplifier is going to use. So this is actually a conceptual realization of that distributed amplifier. You see LX here in the middle, and then L1, and then these are just transmission return lines, the grounds that are shown in black. That's just the bottom part of a 2-stage DA. This was implemented in a 40 nanometer TSMC process, and it has an extremely small form factor. Okay, so the total active area is 0.15 millimeters squared, making it possible to integrate this and use this as an IF stage, say, in a receiver. This has 30 gigahertz of bandwidth. All right, so it's roughly 25 gigahertz to 55 gigahertz. And he got some nice data here. This, long story short, this S12 that shows the bandwidth of this circuit, and then the S11 is more or less the matching that we get out of this device. A little bit about the measurements. They're actually very complicated up in the millimeter wave band. The equipment is extremely expensive. UW has been very kind to me, certainly in the beginning, helping me establish this lab that where we can actually do these kind of measurements. It's one of the few places in the country, one of the few universities where you can take measurements in this band. This is up on the 4th floor. Right here, you're looking at in excess of $1 million worth of equipment. That is a high-frequency probe station. We can actually put devices in there, and with the right equipment, you can measure up into the terahertz region. And then that equipment on the rack in the back, that's roughly like $1 million right there. Or what you see down here, this network analyzer, the centerpiece there, that's a very expensive piece of equipment. Anyway, this is what we have in our lab, and it allowed us to characterize these devices here at UW. That first chip I talked about, measuring it was very difficult. We did not have the equipment at that time. We actually had to do everything through Broadcom, and it was a very challenging experience. Anyway, these are some standard metrics, noise figure, IP3, OIP3, basically a measure of linearity and noise performance. It was difficult to do a comparison. We have a paper coming up at the RFIC Symposium IEEE in Florida. This paper has been nominated for an award. I don't know if we'll get it. We won't find out till later. But it's difficult for comparison because there's not really a lot to compare to. We just compared to very broadband circuits. And in terms of fractional bandwidth, if you look at this 4th row right here, fractional bandwidth we get out of this guy is 77%. So it's very high, much higher than we had for transformer-based feedback. All right, and noise figure was actually quite low relative to other publications, or sort of in line. And again, this was in a 40 nanometer process. Now, it turns out for our broadband millimeter wave receiver, we did not end up using this. What we realized is we went through all these transformations, and to make a long story short, this device was built to match to 50 ohms. All right, that's the standard that you need to use in the lab. But when in the lab, because all the equipment is set up to measure the network analyzer, the signal sources, they all assume a 50 ohm match. Now, when I take this and put it on chip, say for an IF stage, I want that impedance to rise significantly to get more gain. And what we realized later in the game is that if you try to do that, then the size of this distributed amplifier again grows. But actually, I thought that a lot of the concepts were very interesting, and there's actually other applications where you could use this distributed amplifier right at the very front end of a receiver, maybe in the for satellite communication. And there's some other interesting applications, and this chip actually has a lot of interest. But going forward, again, we wanted this very broadband receiver. So the last part of my student's thesis or work was really looking at gain equalized transformers. And again, going back to different ways of resonating a node and then trying to DQ it and broadband it, people over the last 10 years have been exploring, just using straight LC, trying to develop multiple resonances by having 2 LCs and then decoupling those and create 2 peaks that resonate at slightly different frequencies. And then, more recently, integrating a transformer. And it actually turns out a transformer is very broadband. Okay, so now if you model a transformer, this is some work done by my student and others. This is not necessarily new. But long story short, a transformer, both the input and the output, have an effective inductance. They're called an even and an odd mode. They created an even and an odd mode resonance. They split the resonant frequency. So it effectively looks like one inductor at the input and another inductor at the secondary of the transformer. And it creates 2 resonant peaks. Those 2 resonant peaks, I can control the frequency that they're at by design, but I can't control the Q and make the Q the same in both those peaks. And what's worse yet, I can't equalize the amplitude just out of a straight transformer. So a new technique that people have been looking at, actually just one other person, Ashan Afasari at Cornell, had a paper about 2 years ago that we noticed that used this technique to broadband a VCO, to get a very broadband VCO. And the idea is you start with a transformer, and this is the one that will give us these 2 uneven peaks. All right, and now I want to even those peaks and make the Q the same. And I add another mode of coupling. So a transformer is going to give you magnetic coupling, but now I'm going to add a capacitor around that transformer, and now I have both magnetic and electrical coupling. It gives me another degree of freedom. All right, and so my student actually looked at applying this technique in the signal path, not for a VCO, but to broadband the signal path. And he came up, long story short, you're interested in the trans resistance of these transformers when you put them in the signal path. So V out over I in into the primary. So I in goes into the primary, V out comes out the other side, so it gives you a trans resistance. And these are some equations that he modeled to describe the resonant frequency and the location of the peak and the Q. All right, and so in this technique, you can keep the Q of both of these resonants the same, and you can equalize the peaks. That's the important feature. So one way you can look at this, we just laid out a transformer without electrical coupling, i.e. the capacitor that wraps around. And what you see here in red is this is from an HFSS extraction in a 40 nanometer TSMC process. We laid out the transformer, we extracted it, modeled, et cetera. And that's very typical of what you see in red. That's not what we want in our channel. Otherwise, if you had something like this, the amount of equalization that you would need back on the digital back end would be fairly complicated. We'd like to keep this fairly flat. And so after applying this electrical coupling, he was actually able to even out these peaks. And he, in terms of the transformer, this is what the layout actually looked like. Again, this isn't a 40 nanometer process. You see just a slight amount of magnetic coupling. So the primary and the secondary aren't quite over, they're not 100% overlapping, they're just slightly overlapping. That's to control the Km, which actually did the magnetic coupling coefficient. And that helps determine, again, the location of the peaks and how we equalize the amplitude. So then on the side there, you see those 2 little combs. Those are the capacitors that are providing electrical coupling. So he applied this technique to realize, again, something with a 20 gigahertz channel bandwidth that was from 50 to 70 gigahertz, and then down converted this through his receiver to baseband. And this is the actual chip block diagram. You see the input matching network. There's a 3-stage LNA. Each stage is using this gain equalized technique. It goes through a mixer, 2-stage amp, and then another mixer from IF down to baseband. The LO generation, the oscillator is brought in from off-chip using a signal source, but what's important is the LO generation and the buffers that drive these mixers, they are on chip. Again, the whole reason we're doing this going through all this pain of realizing this wideband IF is to lower the frequency of this guy. So we want to be able to capture what the power consumption is of this guy, the first LO in particular. That's the one that will array through this if we realize a phased array system. This is just a description. It's very important to model all the parasitics in these devices. I tell people, You know, everybody brags about the stocks that they do really well on. They never talk about the stocks that tank on them. We actually had a set of chips before this final chip where we taped them out and we got them back, and they actually didn't work very well. And really what it is, at these frequencies, everything becomes a parasitic. It becomes a parasitic inductance and capacitance. So you really have to extract everything and do an electromagnetic extraction using something like HFSS, build a model around that, include all the bias lines, everything. And the simulations are quite complicated. Anyway, this is just to show that we captured as much as we could. And actually what we ended up simulating and designing and what we measured in the lab, pretty much dead on the second run. So this just shows, you know, the actual components. This is the LNA, where you see the GM stages, and then you see these gain equalized transformers cascaded several times. And then this is a 30 to 50 gigahertz IF stage, so very high fractional bandwidth again. And then this is just how we do the LO generation. Nothing necessarily new here. These techniques have been around for a good 10, 15 years. We were just really trying to capture how much power it would take to drive these mixers. Now, the interesting thing I think about the entire receiver is that, remember, each of those gain equalized stages, they're giving us a pair of split resonant peaks, all right? And then what we do is we cascade that, you know, several times down the receiver chain. And by design, it's a little like a filter design. If any of you have done filter synthesis, like a biquad filter, using biquad stages, you have what? Set up holes, and then you cascade that several times to realize a Butterworth or a Chebyshev filter response, whatever it is that you want to build. Well, this is a similar thing, right? So each one of these stages by itself is giving us a set of split peaks. It's a second order response. And, I'm sorry, fourth order response. And then by design, we pick those peaks as we move down the chain so that the overall response is a flat, gives us a very flat response. Okay, so this is the actual chip right here. I noticed I'm starting to run out of time. A little bit about the measurements. Again, this is, so what you see here, the big piece you need to use is this network analyzer. Bring in the bias. We actually probe the chip, and these are high frequency probes on both ends. So we can get an idea of the frequency response of this device. This is the actual chip. You see the LNA, the RF mixers, the IF, the LO distribution. And then these are the probes on that big probe station landing in. We're looking through a microscope right here. Now, as far as the frequency response, this takes a little bit, again, doing this quickly is challenging, but we're trying to measure from 50 to 70 gigahertz and at baseband. And so what you're looking at is the top plot is the upper sideband brought down to baseband. So equivalently, it's 0 DC maps to 60 gigahertz at the front end, and that 8 gigahertz is 68 gigahertz. Now that's the limit of the measurement equipment our lab set up right now is 68 gigahertz. So that's the high end of the channel. The channel goes beyond that. We think it goes to 71 or 72 gigahertz. And then this is the lower sideband from 60 gigahertz down to 50 gigahertz, roughly gives us about 8 gig. So we're somewhere between, you know, again, we're working on the measurement. We actually have the equipment now to go beyond 68 gigahertz, but the setup is quite complicated. My students are working on that right now. But we think it goes up to, you know, 72 sort of gigahertz region. So we're talking about 18 to 20 gigahertz of a measured channel bandwidth. That's significantly more than I think anything else that's been published before. Again, just standard set of measurements, noise figure, et cetera. The big thing here, again, the LO distribution, particularly this 21%, that's what when we build an array, that's what's going to be multiplied quite a few times. And again, we're running this at a lower frequency compared to, say, something like a direct conversion receiver. Now, this is compared to recent phased array publications in silicon. And so the key metric that we thought we would compare ourselves with, our figure of merit, is really power per bandwidth. More often you see a number like this for like wireline transceivers in joules per bit, but we don't have the digital back end. It's just the very front end, and it was, I think, a fair comparison. We compared on a per element basis. So we ended up with 66.1 picowatts per hertz, and that compares quite favorably to other publications here. There's one publication that's actually lower than ours, but he brought in the LO and drove the mixers directly using a signal generator. So he has no LO power to speak of. Basically, he didn't measure it. And so anyway, we included it, but we just thought it's not quite a fair comparison. I think if you included the LO power, we would be significantly lower. All right, so then there's this idea of coexistence. Again, I guess I'm running out of time, but the big thing, that's one topic that's of interest is it's a problem that we've had for a good 10 years, like a WCDMA, Qualcomm's WCDMA system. It's called full duplex. So it's FDD, so you're transmitting and receiving at the same time, okay? So if you imagine this, I have a receiver, I'm very far from the base station, I'm detecting a weak signal, and I'm trying to transmit a very high output power signal. So this leads to a really interesting problem in the receiver, is that the transmitter can leak over to the receiver, all right, and it can cause a lot of problems in terms of gain compression, interference from reciprocal mixing, phase noise, and also create, through nonlinearities, can create interference by creating new spectrum in the received path. So a hot topic at the moment is, how would you deal with this? The one method of doing this is you have a discrete filter. They call it a duplex filter, but that's very band specific. And going forward, we would like things like software-defined radios, where we don't have specific front ends. We could program it and move around to whatever frequency possible. And further, that filter actually costs quite a bit in production. We'd like to integrate it, that function somehow in silicon. So this is something people are focusing on at the moment. There's been a lot of talk at Rice and at Stanford where we talk about transmitting and receiving in different bands. Now, right now, if I have something like a Qualcomm CDMA or GSM, there's this duplex band that's put in there. It's a guard band, and it's just a dead zone. It's not being utilized. All right. So what we'd like to do is come up with methods that allow us to transmit and receive very close together in frequency, and use that spectrum, and then even going forward, putting both the receive and the transmit bands on top of each other. So from a theoretical, more of a networking and communications theory perspective, there's a lot of work at Rice and Stanford on doing this. What I'm interested in is sort of the nuts and bolts. How would you do this in silicon? All right, how would you actually build this thing? It's actually a very difficult problem. And so I think it's pretty interesting, some of the work that my students are doing. Tong Zhang has been leading an effort. Apsara was working on this chip I'll describe in a moment, and Andrew and Shansi have just joined this project. They're looking at more of the transmitter side of things. We have a chip. It's one of the first of its kind. It demonstrates doing cancellation. So we know this transmitter somehow is going to leak over the receiver. But now if I could deliberately inject a component of that transmit signal into the receive path and phase and amplitude match it, I could cancel it, all right? But again, doing that in silicon is challenging. Ideally, what would we like? This guy, if we want to inject something right at the input of the receiver so we can relax the performance we need out of the first active devices, the LNA, the mixers, et cetera. So we want that cancellation as close to the antenna as possible. It has to be low noise. All right, any noise I inject at the input of the receiver, that adds directly to my noise figure. That's really a difficult problem. Again, we're trying to detect signals like in the cell phone, microvolts at the antenna, very small signal. So ideally, the implied characteristics of this canceller is that it's noiseless, and it uses no active components, transistors, or even resistors, which generate thermal noise. So there are about 5 efforts worldwide, and I'm only aware of 2 groups in the world, our group and USC, that is kind of realizing this. Everybody's trying to do active cancellation, but at the input of the receiver, it'll destroy your noise figure. So this also implies, ideally, that the network is both, the network this cancellation network, is passive and reactive, i.e., it's only realized with L's and C's. Well, it turns out, a little trick that we pulled, is you have a transformer typically at the input of a receiver that you use there anyway for impedance matching. All right, you got to match a 50 ohm antenna. So it's just what you see on the right there is the transformer, and then conceptually, this is the diagram here where we have the transmitter, and then you'd have a transformer that you'd use for your matching network, but then in that transformer, we add 2 parasitic primaries. You can think of it that way, where we tap off the output of the transmitter, we go through an attenuator. We want to attenuate because this is a very high-powered signal, and attenuate shown in green there, so that's what we're deliberately injecting. And then shown in red, That's this undesired signal that leaks from the transmitter over to the receiver. And then the blue at the input of the receiver, that's the signal we actually want to get. We want to receive that. So they're coming in this primary path through the RX antenna. We deliberately inject this green, and we put an opposite phase to the transformer. So conceptually, well, actually, this is kind of halfway between conceptual and the real implementation in silicon you see up on the right there. You can think of it as electromagnetic cancellation. I'm deliberately adding a field in the opposite direction that cancels the red that's going through the RX path using this green primary in the center there. So my student Tong and Apsara, they actually taped out a chip in a 40 nanometer process. Try to make a long story short, that's the model of the canceller up on the right with the path, the cancellation path that's used for amplitude adjustment, this array of capacitors here. Up on the top, that is another primary. I haven't said too much about that. That actually helps us adjust the phase of this signal, this TX cancellation path signal, and adjust the phase as it goes into the receiver. So I'm going to phase match with that leaked component. My student recently built some models on this. I'll probably, in the interest of time, kind of go through this. This was the actual chip where we had what I call a PA emulator and the PA matching network on chip, and then the receiver input, and then this cancellation path here. We actually took a set of measurements, both with a real duplex filter and without a duplex filter. And one would emulate what you would do today. You'd probably have that duplex filter, but in the future, we'd like to get rid of that. This is the actual chip. You see the canceller up on the left here, and then you see this PA matching network and the LNA. And this will be at the RFIC symposium in June. The amount of cancellation that we were measuring was designed for the specific case of the WCDMA band, because this is one area where it would have direct application right now. But again, in the future, we want something that's very broadband. We get a flat 23 dB of cancellation over the TX band of WCDMA, and that cancellation holds for different power outputs. That's very important because sometimes they vary around. Most importantly, this shows the noise figure of the receiver with the canceller off and on. All right? No impact on the noise figure. This is quite a bit different than, there's only one other publication, just came out in February at ISSCC, that tries to do this cancellation using active components, adds significant noise figure in using active cancellation. This is this long-range sensor radio concept. In the interest of time, I think I'm just going to breeze through here. Basically, it's a new type of transmitter that would enable very long-range sensor data communication through the chip. We had a device, this was in my first couple of years here, both Venu and somebody, Will Wesson, who is now at Google designing chips in the Bay Area. They came up with this very interesting PA that actually modulates the real part impedance at the output of the power amplifier. And long story short, what that allows us to do is eliminate the voltage regulator, the losses of a voltage regulator, and attach it directly to an energy storage element. So we had a number of publications out of this, actually quite a few. RFIC Symposium was a big one. We had a JSSC paper, and Communications Magazine this month, they were interested in this chip. I have a paper with Venu and Will in this month's issue. Okay, so the last thing I wanted to talk about is this joint project. Again, with the medical school, it's funded by the NIH. There's a big group down there, Professor Hauk and myself. We work with that group in different parts of the electronics. They're trying to miniaturize a PET imaging system, okay? And so part of this is, the new thing here is that, and this is my student Samrath Day, who's been leading this effort. Detectors have moved from a vacuum tube type detector to silicon. And this has happened in the last maybe 8 years. So what this allows us to do, we've shrunk the detector, and we can now make this array. We can pixelate it more, all right? So we can have a lot more detectors and a higher density of detectors. So that's a good thing from an imaging perspective. But from the perspective of the electronics is, now these are some examples of these arrays. And if we go inside, now each detector needs its own channel, electronics, and then it goes through actually a cable through that big tube we just saw a second ago, and it needs a dedicated ADC, and then before it goes into the DSP, where we'll do signal processing. Well, an architecture that Scott Hauk and myself and these guys down there have been exploring It's a way of reducing the number of channels, but you can think of it being analogous to memory. So each detector does not have its own channel going all the way back to the digital. We combine rows of detectors and columns of detectors, and that gives us spatial information, and then we get timing information by a common channel that's shared by all of these devices. And there's some interesting stuff in the electronics, but I'm going to actually skip through that. We actually just got this chip back last week. So this was fabricated at TSMC. It is an 8x8 detector array that uses this row column architecture. So you see the individual channels, and then these channels are shared in a common row and a common column, and then it goes off chip. And my student's actually working, Samrath's working on the board right now with the medical school. And then this last area, this is a project, again, both Eric and Daniel have been working on through the Neural Center. How do we implement the stimulation electronics in standard CMOS? This is actually, they call it the neural chip, but it's a board. And they use it for stimulation for ECOG, like brain surface stimulation and spinal stimulation. It's actually not a chip, it's a board. All right? It's a small board, it's only about that big, and people put them on the top of rats' heads, et cetera. But this is the extent of the state of the art in terms of making this electronic smaller. Well, there's been a lot of publications on how to do recording in CMOS, all right? And you can hear groups like Biomedical, and then if you can do that in CMOS, you can combine it with some neural DSP. But the stimulation electronics people have tried, but they've been in specialized processes, high voltage processes. Long story short, if I want to stimulate a cluster of nerves, I got to inject some charge into the cluster of nerves, and I actually need to suck the charge back out so I don't damage the tissue. You're injecting a current through an electrode that interfaces this tissue. Those electrodes have very high impedance. Inject 1 milliamp to 5 milliamps, depending on the application. It works out to, it's tens of kilovolts for the electrode, tens of kiloohms. You end up with 30, 50 volts. All right, so how do you do this in 1.5 volt standard CMOS process? If you could, you'll collapse that last difficult piece to integrate, the stimulator, with the recording and the DSP, et cetera. All collapses into one chip, very easy to implant in the body. Anyway, I need to wrap it up. There's some just very cute tricks on how to use. My students are working on this chip right now. It's an inductorless dynamic V2V charge pump. Long story short, they come up with a scheme where each individual transistor in there does not experience a voltage terminal to terminal greater than 1.5 volts. Right, but then they're building up a voltage by stacking these elements of a charge pump. And there's some other cute tricks that are in this system that are actually very beneficial towards neural applications. Mainly, this can dynamically adjust to any impedance looking into the electrode. And that's something actually that's a mission sort of the Neural Center. Anyway, my students hope to tape out a chip this summer. I hope they do too. We had an initial chip that had just the voltage regulator on it. This was a 65 nanometer CMOS process. The regulator, part of the stimulator, that's the only piece. It's not the whole stimulator. It's in the center. Neural recording from Brian Otis's group is on the left, and Josh Smith's group on the right has the wireless power transfer. We want to integrate that all eventually into one chip. That's one of the missions of this center. Anyway, my student Eric got some nice data just from the regulator portion. We have some new schemes. These are new methods. My students are doing an experiment right now to do a differential stimulation that has advantages, again, to integrating in CMOS. Eric and Daniel are working with Chet Moritz and Steve Perlmutter down in the medical school. I think I'm going to wrap it up because I'm over time, as usual. But anyway, I think hopefully I've impressed on you that chips are going to play a big role, whether you're interested in software or hardware. Chips are going to play a role. It's going to enable a lot of these applications, big data applications, and new areas to develop software. So.
Okay.